Hello everyone and welcome to this lecture. In this lecture, first we will see a very beautiful product of two graphs that we call Cartesian product. Okay, and why we are doing so? Remember, in the last lecture we have learned one technique to generate co-spectral graphs, and that technique was nothing but we call GM switching, and it gives co-spectral graphs with respect to adjacency matrix. By the way, it does not guarantee that the graphs will be non-isomorphic. Okay, and we have to check this non-isomorphic thing separately, right? Okay, yeah, but the eigenvalues are same with respect to the adjacency matrix. Okay, so today first we will learn a new product that we call Cartesian product of two graphs. Okay, and we will see that how we can make use of Cartesian product to generate or to give some co-spectral pairs. Okay, so let us start with Cartesian product of two graphs. Okay, so Cartesian product of graphs, product of two graphs or just graphs. Okay, very good. Suppose we have two graphs, two simple graphs. Suppose this is G, okay, with vertex at this and edge set this. Okay, and there is another graph with vertex at this, okay, and vertex set edge set h. Okay, let me first give you an example. Okay, give you an example of Cartesian product of two graphs, and then we will define it formally. So suppose one graph is this and another graph is this. Okay, and let me number them. Okay, so let me label these vertices 1 2 3, and for because for the defining purpose of Cartesian product of two, I kind of in making different labels so that it is clear what as we will see the definition, the why I am not putting them 1 and 2. Okay, in fact you can do so, but by writing AB it will be more clear. Okay, now the Cartesian product of these two graphs is nothing but it's a graph on 3 into 2, 6 vertices. By the way, so we will make all pair of choosing one vertex from the first graph and another vertex from second graph. So how many pairs we can make? 3 into 2, okay, that is 6. Okay, so these 6 pair are this, right? So first is 1A, okay, so you can call 1A, then 1B, okay, 1B, then what is 2A, then 2B, okay, then 3A and 3B. Okay, now do this and just focus on the drawing of how I am doing. Okay, one is one same, so AB has an edge. Very good. In fact, all these will be having edge, and then this A is same, so this A is same, so this. Okay, and very good, and similarly this. So this will be Cartesian product of. Just look at it. Okay, and now let us formally define it. Okay, so basically what is happening is, so let me write, so Cartesian product of G, that we will denote by G box X. So the Cartesian product, so this is, so we will denote it by the box. Okay, is a graph, is a graph on VG cross, this is again Cartesian product, okay, of vertices, right? Basically you take pairs, one from VG, one from vertex, one from VG, one from VH. Okay, so these many vertices below, that's why here there are 6 vertices. Okay, very good. And then suppose there are 2 vertices in this graph in J. So 2 vertices, so let me actually write here. So suppose this is your G. In this G there is UV, this is G, and this is H, this is maybe WZ. Okay, so 2 vertices, then comma 2 vertices. Okay, suppose these vertices are UW, because now vertices are in pair, right? So UW will have an edge, so this will denote as with VZ if, okay, so the condition if U equal to V and W is having edge with Z in H, right? Or what if these two vertices are same, basically W equal to Z, okay, W equal to Z, and so maybe you can call in H, right, in belongs to H, this H, okay, and then U and we have an edge in G. Okay, so this is a very very simple definition. You just now maybe with this example it is now more clear. Okay, now we will see an interesting thing. The this Cartesian product of these two graphs G and H. Okay, how can we find these eigenvalues of G box H? Okay, we will see there is a very very nice structure of eigenvalues of G box H, and these can be given by the eigenvalues of G and H. Okay, in fact the eigenvalues of G and H are this. Okay, so let me write the theorem and we will prove it. Theorem is this: let G be having the eigenvalues lambda 1, lambda 2, and let's suppose, okay, ordering here actually doesn't matter here. So lambda n, so suppose there are n vertices. Okay, so and H be having the eigenvalues, what maybe mu1, mu2, okay, and mu m. So there are m vertices in, so there are n vertices, m vertices. Okay, then the eigenvalues of the eigenvalues of G box H are lambda I plus mu j, okay, for I greater or equal to 1, less or equal to 1, and j greater or equal to 1, less or equal to m. Okay, so basically just basically you take one eigenvalue from A, one eigenvalue from suppose G, one eigenvalue from H, and add those. So all possible such additions, right, will give you all the eigenvalues of this. How to prove this? Okay, so let us prove it. Very very beautiful. Okay, so prove it. Proof. Very good. And by the way, the adjacency matrix of G I will take as what we call maybe A. Okay, so A is actually the adjacency matrix of this, B is the adjacency matrix of H. Okay, for simplicity. So these are the eigenvalues lambda 1 up to lambda n, and here the eigenvalues are beta 1 up to sorry, not beta, mu. I have used mu here, so sorry. So okay, mu 1, mu 2 up to mu n. Okay, mu m. Very good. So now suppose we have an eigenvalue here lambda of A, and similarly there is an eigenvalue of of B, mu, okay, with corresponding vector y. Okay, very good. Now what? Let us define a vector which is this. Okay, so which is actually this. Let me denote by x cross y. Okay, so this is a vector of size of having so a vector. Let us define a vector. Let me write it more clearly. Let us define a vector. Sorry. Let us define a vector. This is maybe x cross y having n cross m entries, okay, entries, and okay, so there are n m entries and this. So in fact this. So any entry of so basically if you so suppose okay, with respect to, actually let me write some of this again, this same graph G and H. This is U V W Z. So W U W entry here, U comma V is nothing but X U and YW. Okay, so this is very well defined. Okay, so there will be how many entries? N cross M entries. Okay, and these will be corresponding to all these vertices here. And suppose I am defining this vector as this. Okay, now you see that we will prove that this indeed is an eigenvector. This indeed is an eigenvector corresponding to what we call this lambda plus mu. We have to prove this. Okay, so let us see how we can prove. Okay, now you see that for any edge, suppose you take this u w in which belongs to basically, maybe in more preferably I will write an edge in, suppose this. Okay, so what will be the equation by this, right? What will be the equations for any as this? Okay, so let us see what will be the quantity this, right? We have, if you, so basically summation, if we write this quantity x this, okay, and all the neighbors, you see all the neighbors in of UW vertex in Cartesian product of G and H. So suppose this all the neighbors are this, the neighbors, maybe I can just write by this notation. So all V comma Z which are neighbor of, so suppose which are neighbor of U W. Okay, so and you actually take this quantity. So what will be this? Okay, so this will be nothing but this quantity, right? So summation over, we know that what is this, right? So summation over this is xv and x yz. Okay, and these are all the neighbors, right? So over all the neighbors of uw, right? So this is vz, okay, vz which are neighbor of uw. Okay, very good. Now this can be written as in the summation of two terms. So and these two terms actually follows from the definition of Cartesian product of graph. So this can be written as this. So suppose these two vertices are same. Okay, suppose this is u and z, which is again u and w. In that case, z and w must have an edge, right? So must have an edge. That's why this will have an due to the definition, right? So so in that case, what will be this? So xu, so this is xu and yz. Okay, and another term could similarly we can write is this, right? So in that case, suppose this is equal to, the second term is equal to w, so basically v w. Okay, and then it will have u w, right? Then okay, so we can always break it. So in that case, what will be here? So it will be xv. Okay, and this will be y will be w, right? Very good, very good, very simple thing. Okay, so now I can write this equation as this. So this is nothing but summation over z is an having edge with w, and this is xu yz. Okay, and then plus similarly this v is having edge with u. Okay, v is having edge with u, and so this is xv yw. Okay, now you can easily take, because this quantity is independent of xu. So now basically you can take xu outside here. So summation over yz, z will z is having edge with this. Very good. Now plus again you can take from here yw outside. So this will be xv v. Okay, now what we can make use of this? Okay, let me again write the same thing. So uv are in here, wz are here. Okay, very good, till now it is fine. But you see that what is this quantity? What is this quantity tells? And similarly, what is this quantity telling? Okay, this is nothing but, you see that all the neighbors of z, and yz is what? It's eigenvector of, so basically y is an eigenvector of what? So this is h, this is g, y is eigenvector of h, right, and x is eigenvector of g, right? And this tells that the jth entry of this vector, right? This jth entry of this vector, okay, and this is given basically no. So this is what this will be give you. So basically, let me write. This is nothing but by equal to mu y, right? Mu y. Okay, don't confuse it by u. This is mu y. Similarly here, this will be what? Ax equal to lambda x, right? Now you see that a summation over all the neighbors of w, right, which are z's, right? So this quantity will give you indeed this, right? By the definition of here, this quantity will give you x u, okay, and then if you see clearly here, because this is over this vector and then all the neighbors of w, so this is nothing but mu times yw, okay. Similarly, this quantity will be what? Yw times, this quantity will be similarly, if you see here, all the neighbors of u, right? So this will be lambda xu. Very good. Now you see, now what? Now it is very easy to write. Now you can write this as xu plus lambda, then xu and yw, okay. Okay, very good. And let me check what it gives. Oh, great. So you see, this quantity is nothing but this, right? So wow, so mu plus alpha, this is nothing but x, this cross or whatever product you say, this is nothing but u vth entry, right? U comma vth entry here. Now this is what? You see that this is again eigenvector structure. So this is a vertex ub, this tells all the neighbors of this, and on corresponding entries corresponding to neighbors, this is adding, right? So this means this is an eigenvector of corresponding to ub, and the matrix corresponding to this is basically g, whatever the adjacency matrix of this will be, right? So this is nothing but the, so basically let me write it. So that means this implies that x cross h implies that, so basically adjacency matrix of G box H is times, so basically now you can write this vector x, okay, so this is a vector, okay, this vector equal to mu plus lambda x, okay. So this proof. Very good. Okay, so maybe at one so there are slight calculations, but I hope, I mean, it is so once you draw the graphs and play with the small graphs, and it will be clear how the proof is following. Okay, very good. So now what? So we know the eigenvalues of Cartesian product of two graphs, okay, in terms of the eigenvalues of their individuals. Okay, very good. Now how can we make use of this to find a co-spectral pair? I will tell you a very beautiful co-spectral pair, which is indeed so non-isomorphic graph, but they have the same eigenvalues, and it follows from GM switching. Okay, so let me now actually take the case of Cartesian product of K4 with K4. Okay, so K4 is complete graph on 4 node. Let us take Cartesian product with this. Okay, so what will be this? Okay, so let me actually draw it. Okay, the picture will be slightly clumsy because there are many vertex will be here. So suppose this is these are 4 vertices here. Okay, these are 4 vertices. So let me first name the 1, 2, 3, 4. Now these are corresponding to what? These are corresponding to just one copy, right? Now in this way there will be, because this is a dot product, Cartesian product of K cross K, so there will be 16 vertices. So now let me number them: 1, 2, 1, 3, 1, 4, then 2, 1, 2, 2, 2, 3, then 3, 2. So this will be I made mistake. Okay, so this will be what? 2, 2, 2, 3, 2, 4, then 3, 3, 3, 4, okay, 4, 1, 4, 2, 4, 3, 4, 4, okay. Now you see that now I can put the edges with the definition of Cartesian product. Okay, so there will be edge like this, right? Then this, okay. So Similarly here, I hope I'm not missing anything. Very good. So okay, very good. Then yeah, very good. Yeah, great. So every vertex at degree 3 up to now. Now similarly you have to do below also, right? So this, then this, then this. Okay, I hope I have drawn everything. Yes, yes. Then okay, very good. And then yeah, maybe this. Okay, I hope I have drawn everything here. Very good. Okay, then this, then this. Okay, so this is K4 box K4. Okay, now let me highlight these two four vertices here. So suppose this is 1, these are red. Okay, red in red colors. Okay, now what you see, okay, now what you do, by the way, what will be its eigenvalues? Let us see first eigenvalues. Eigenvalues of this graph will be what? Okay, eigenvalues of this graph is nothing but, see, what are the eigenvalues of K4? K4 eigenvalues are this, right? 3, then -1, -1, -1. There is another K4, so again their eigenvalues will be 3, -1, -1. You pick one from here and add those, right? So basically the eigenvalues of this graph will be, so 6, this by adding this, then by 3 and -1 this will be 2, and then -2. So how many times this eigenvalue will be? So this will be 1 time. How many times 2 will be coming? I think this will be coming 6 times, and then this will be coming 9 times. Okay, so these are the multiplicities. Okay, very good. So now what you do, now remember GM switching. Okay, remember GM switching. Okay, what you do, you take y edge the red vertices. Okay, these red vertices are nothing but this. You see that what are these? 4, 1, it's okay, 1, 4, 2, 3, these are nothing. 1, 4, then 2, 3, then 3, 2, then what? 4, 1, right? Very good. And x as rest of the vertices. Okay, x as rest of this. So this set x as, so basically x as the rest of the vertices. Okay, now you see that rest of the, basically if you see the GM switching, there are x, so there is just one partition that, and that is special partition, right? X, y. Let me do it with a capital Y. Okay, very good. Now what? You see that here, or maybe I can take x as, maybe now let me do it in that way, it will be more apt. Okay, so x as your these vertices and y as the rest of the vertices. Okay, so let me basically, now you see that, so this is your yeah, now you see that in the y, so y are these vertices, right? Every y here, okay, every vertex y, every vertex in y is had direct edge, or maybe is adjacent to only 2 of the red vertices. For example, here if you take 1, 3, okay, so 1, 3 has an edge with 1, 4 and 2, 3, but none of the edge with 3, 2 and 4, 1, right? Okay, what your GM switching does? So whenever there were edges, you remove those edges and connect to rest of the vertices, right? Connect the basically make that vertex adjacent to rest of the vertices. Okay, so basically now in the GM switching, what will happen in the GM switching, these two edges, let me write with brown. So these edges, for example, this, let me give you this edge will be cut and this edge will be cut. Instead of this, one will be connected to this, 1, 3 will be connected to this, and again will be connected to this. Okay, and do this for every vertex here. Do this for every vertex, right? Now the resulting graph we called Shrikhande graph. Okay, resulting graph we called Shrikhande graph. The graph after GM switching, is known as, in this particular GM switching of K cross of K4, box K4 is known as Shrikhande graph. Very, very interesting graph with very, very beautiful properties. Okay, and by the way, why these two graphs are non-isomorphic? Think about it. Why they are non-isomorphic? I mean, first draw the Shrikhande graph. What will be its picture? Okay, the hint is that in K4, box K4, there will be a K4. Right? Inside there will be a K4, a complete graph, a click on K4 vertex. Okay, but in Shrikhande graph there is no click. There is no click on 4 vertices. Okay, so these are non-isomorphic. So and Shrikhande graphs are non-isomorphic. Very good. So we have seen a very, very nice use of GM switching to generate a graph. In fact, a very, very well-known graph that we call Shrikhande graph. Now, in this way, I deliberately actually have taught this Cartesian product of two graphs, okay, because the eigenvalues are immediately derived from the original graph G and H. Maybe we can make lots and lots of families of co-spectral graphs. Okay, what you do, so maybe you can come up with different pairs of basically the graphs such that the eigenvalues remain same, and maybe those pairs are actually non-isomorphic. Okay, so there are a lot of possibilities with Cartesian product. Okay, so we will see many example of co-spectral graphs in our tutorials and in our exercises. Okay, so I am stopping the lecture here. So thank you very much and see you in the next lecture.